For this last video, we're going to take a look at the trees data set. R comes prepackaged with a lot of data sets that are just always open, always around, good for case studies and things. Just so you know, trees is always available. It's right there. You just type trees in there. You see you've got some data on 31 trees, their girths, their heights, and their volumes. In fact, I'm just going to attach this data set so that when I type girth, I'll just have the girths, and I don't have to type trees $girth if I want to indicate girth, or trees $height to indicate height, and so on. Okay, so let's go ahead and do a regression here on volume versus height plus girth. Okay, now this is our first model with two predictor variables. Okay, this is important, but we'll see this coming up again later. Here I'm gonna have volume versus essentially the way it looks is it's like y equals some intercept plus height variable times a constant plus girth variable times a constant. So I'm trying to model the volume based on these two predictor variables, or these two independent variables. My linear model here would probably be something like a plane slicing through 3 space or something. Okay, so now let's just plot girth versus the standardized residuals there, or sorry, vice versa, standardized residuals versus girth, and you can see that there's sort of a pattern there. It looks like they sort of start up here, and then they spread out and fan out, and then sort of kind of go up and to the right, so that maybe our variances are not constant. This is sort of a problem. Let me make it's not what you want to see when you plot residuals, right? So let me make a couple of plots here on the same window. Let me make a histogram of the residuals and also do a QQ plot of the residuals, and we'll drop a line on that QQ plot. Okay, so that doesn't look too bad. It looks like these residuals might they don't look like they're departing too far from normal. I'm gonna compute something called the skewness, which is a measure of, well, skewness. You know what skewness is, right? If you have something that departs from normal in a way where there's, say, a few observations more off to the right, then you might say that the data set is right skewed. So a large skewness value, a large positive skewness value indicates right skewness. A large negative skewness value indicates left skewness. And I'm going to check the skewness of those residuals. So that's not too huge there. Let me check. So checking for skewness, one way to think of it is also sort of checking for symmetry. Now, here's something that I want to do. I want to load this library called MASS. And I want to do this because in this library we have something called the Box-Cox transformation. Okay, and we just talked about those in the notes, but this is how you get at the Box-Cox function. I want to transform the volume according to Box-Cox. I'm going to use this automated Box-Cox function to find that value of lambda that maximizes the log likelihood function. Okay, so and I'm storing my Box-Cox output in this variable called trans for transformation maybe. You can see what's in there if you just type trans. It's a it's a whole bunch of stuff. But look, there's some x values. There's x trans x values and trans y values. Okay, it turns out these x values are actually the lambdas. These are our lambdas, our potential lambda values. We want to pick the right lambda for the transformation. And these y values are actually the log likelihood values. Okay, so I tell you what I'm going to do is just to make it easier to read, more consistent with what we're doing here with our more consistent with our language, I'm going to store the trans x values in the variable called lambda and the trans y values in the variable called log LH for log likelihood. Okay, and then in fact I'm going to cbind the whole deal there. I'm going to do boxcox. I'm going to store this stuff in a variable there called boxcox. It's I'm going to cbind lambda with log likelihood like that. Okay, and now if I type boxcox, you'll see, or maybe just the head of it because it's kind of long, head of boxcox. There, you see some lambda values and some log likelihood values. We want to find the lambda value, remember, that maximizes this log likelihood function value. And so one way to do that is to order this this structure here, this data frame called boxcox. I guess it's a data frame, right? Is it boxcox? No, it's a matrix. Okay, all right. But I want to order the rows in this boxcox matrix according to log likelihood and in decreasing fashion. Okay, so I can do that with this command, boxcox, that I want to look. It's just the left and right square brackets there. I'm going to keep all the columns, but I want to reorder the rows. Decreasing according to this variable log LH. Okay. And now, so you can see that. You can see that as I scroll up these values here, the log likelihood values are actually increasing. So I want to pick the lambda value that corresponds to the maximum log likelihood value. So this is the lambda value that we're going to want. Okay. So what I can do then is maybe do reg2, regression 2. Another regression model. But this time, run a linear regression model on volume raised to that power of lambda. Volume raised to that power of lambda. Now, if you remember from the notes, the Box-Cox transformation is actually given by this, right? It's you take the y values raised to the lambda power, and then subtract 1 and divide by lambda. Well, sometimes we don't bother subtracting by 1 and dividing by lambda once we find the lambda, because what all you're doing there is shifting by 1 and then rescaling. Okay, so it's not that important. I'll just raise the y variable to that lambda power and then model this on the height and girth predictor variables. And I can actually, if I type plot reg2, this is kind of neat. You'll see actually here's my log likelihood function. Here are my lambda values down here. The lambda value that actually maximizes that log likelihood function is right there at about 0.303. Of course, can't see it. It's a funny little thing here. Well, you saw it for a second there. It was there. I don't know why it's not popping up now, but let's try this one more time. Well, here's standardized. Here's a QQ plot of the standardized residuals for this model. Volume raised to that lambda power. this is some sort of a smoothed regression. Looks like for I'm not even sure what this is. Standardized residuals versus fits. Um, so I think these are indicating potential outliers. Maybe not sure what these are. We'll talk about Cook's distance later on. Well, anyway, if you see that first plot, well, it's gone anyway, but um, but you saw it. If you can scroll back, you'll see that first plot that looked sort of like this away. It's a nice plot of the log likelihood function versus the lambda values. Um, so now maybe I'll make a couple of uh, plots here on the same plot window. Here's a histogram of the residuals for the second model there after using the Box-Cox transformation and a normal QQ plot. Looks like this. And skewness looks like this. It's even less. It's negative now, but it's smaller. Um, maybe I'll do I'll plot girth versus or just plot there we go, plot the standardized residuals versus girth now for the original problem, and now you can see that the standardized residuals, they've actually improved in terms of variation, and they just sort of look a little bit more uniformly distributed across this girth variable. It seems that is, their distributions seem to be a little bit more the same across this girth variable. Here there seems to be a trend this way, sort of like a smile. Okay, and that's what you want to see.